But blood vessels, we're going to learn about how the arteries and the veins, we're going to learn a lot about arteries and veins, how they're made up, what their unique features are, and then we learn about arteries, veins, and then we learn about capillaries, we learn how they look. Those are the ones that do tissue perfusion. And then we go into the lymphatics and how they help the system. I don't know if you have heard of the lymphatic system before. It's one of those systems that's not getting as much attention as the heart and the cardiovascular system, for example. And we briefly talk about the major arteries, the names of the major arteries and the major veins. I'm not going to go too heavy on that because a lot of the names are based on where in the body they are, like brachial, axillary, subclavian, or where they feed blood to, like the kidneys is a renal artery. We'll learn that word is renal. And so a lot of them we can find in the anatomy books that way. And then we finish that chapter up with blood pressure. And then we'll do a lab on that afterwards. Look at, see, I got all these on the line now. So when we look at blood vessels channel blood through the body. They connect areas of substance exchange, which are capillary beds, with the heart, which is the pump that pumps the blood continuously through the body. Arteries, we learned before, lead blood away from the heart. They are high pressure vessels. So what that means is like a hose in water. You have a hose in the water and you turn the hose really strongly on, the water goes very forcefully through that hose. Or you turn it off and it just trickles a little bit. That's the difference between high pressure and low pressure. The arteries are attached to the heart, and so the heart pumps, and so it creates that force, that hydrostatic pressure. So that's a hydrostatic pressure. Hydro means water. Hydrostatic pressure. And it forces that blood straight into the great vessels of the aortic arch, or into the aortic arch, and that's very, very powerful from a force pushing that way that a pump can do. Once the blood goes through the capillaries, which are going to be the areas where there is exchange of substances, the veins carry then the blood back to the heart, but those are low pressure vessels because there is no heart pumping at all. That blood has been slowed down so much that it can seep into the tissues and come back into the vessels. And from there then, the blood has to be carried by the veins back to the heart and has to use other means other than a blood pressure, other than a heart contraction pressure to bring that blood back. And we'll learn a few things why that is. That is, for example, there's valves in the veins like we have in the heart, the same valve sort of thing, the same structural things, like the semilunar valves. And they help the blood to move more towards the heart than falling back down into the legs, for example. The other things that help the blood go back to the heart, talking about blood going to the heart, are then the lymphatic vessels. The lymphatics are the other system that helps us with that, and we'll talk about that when we get to after the veins. When we look at the general makeup of blood vessels, the structure, the artery is going to have to look a little bit different than the veins because the arteries has to withstand a high pressure. The veins just have to channel blood through the body so it goes back to the heart and doesn't end up nowhere. So we need to have the right destination. But they're both made up of the three same layers. They have an inner layer, a middle layer, and an outer layer. The inner layer is also known as the tunica intima, the deepest, or also the endothelium. And we had this term called endocardium. I know it's a long time ago now, but it's in the book somewhere. Endocardium, and that's the innermost layer of the heart. And that is continuous with the endothelium, which is the innermost layer of the blood vessels. That's the layer, that's the endothelial cell, so it's epithelial tissue that's anchored in the basement membrane in the connective tissue. That's an area where we can have plaque buildup in a vessel, that we get atherosclerosis, which is one of those problems with having the cardiovascular system, where you got the plaques throwing, the cholesterol problem that they talk about. That happens in that area. Then we have a middle layer, or they also call it coat. It's known as the Tunica Media. That's in media in the middle, and that's composed of smooth muscle and elastic fibers. Smooth muscle and elastic fibers. So that's kind of cool, because this can assure that some vessels can expand or shrink together. So we can guide blood through the body to areas that need the oxygen and the nutrients most. That's because of the muscle in the vessel. The elastic fiber in the vessel make it so it's elastic. So if you have like the heart coming up into the aortic arch, it has to be able to expand and contract a little bit. It has a little give in it, so it doesn't just break. It's not just brittle. And that's the elastic fiber there. So that's an important layer. And then the outermost layer is the outer coat, or the tunica adventitia. And that's composed mostly of connective tissue and is embedding the vessel in its surroundings. Look at that, we're getting cut off. So a lot of time the outer layer is sort of helping the structure to be sitting where it is, attaching to where it needs to attach, that it doesn't move around too much, that it goes where it needs to go. So that's the outer. It's usually a tough connective tissue. So this talks about the hydrostatic pressure, the hydrostatic force that I was just alluding before. So when the heart ejects the blood into the aorta, it creates this force of about 120 millimeters of mercury. That's why that's the systolic blood pressure reading, the higher reading. Arteries have well-developed tunica media. That's the muscle part, right? Media is muscle. That either contract or relax to regulate blood flow and blood pressure. Regulate blood flow and blood pressure. So you can get high blood pressure because you got too much constriction in the blood vessels. That could give you high blood pressure. And regulation of blood flow is, well, if you're running around, you're going to have a lot of blood flowing to the muscles, so the vessels will bring the blood to the muscles and not the stomach. That's why you don't want to eat and then go running. Because that's when the body needs to have the blood going through the gut area to bring the nutrients into the system that we just ate. And so that's where that logic goes a little bit. Vaso means vessel. Constriction versus dilation. Constriction means when it is not as open. Constrict, shrink down. And dilation means when it's open, more open. Patent. So this is a relaxed muscle, this is a contracted muscle. Elastic fibers embedded in them in the wall stretch slightly. We talked about that a little bit. So they give it some give, which when the blood is forced into them, they recoil when the heart it relaxes, which pushes the blood forward, assuring continuous blood flow. So that's a very interesting sort of concept. So when I force blood into the aorta, right out of the heart here, this is the aorta, then the force of that hydrostatic force pushes the vessels further apart. And that elasticity in that is like a rubber band. It lets it give a little bit. And then as the force of the heart, and the heart relaxes, there's no more blood force coming. And at that time, the push is not stretching those vessels. The non-push, the lack of push will bring them back together. They recoil. So the vessel will shrink in a little bit, and the elastic fibers, it's like a rubber band. You let it go, and it recoils. It goes back to its original length. That's when the heart is not contracting. So when it's contracting, that we call that systole. We talked about that, right? So when the heart is in systole, this is happening. When the heart is in diastole, then the recoil is happening. And that helps, that elastic recoil helps to guide the blood in a continuous flow through the body. Otherwise, it would go like, you know, what was it, about 70 milliliters, more or less, per stroke? 70 milliliters, nothing. 70 milliliters, nothing. You can't do it that way. So that doesn't happen, that blood always flows, is we have this system here. So that's pretty cool. And then, as I mentioned on the previous page, the capillaries is when we have a substance exchange in the capillaries. So that's when we need to have no more force, no more blood pressure going through those vessels. Because, well, a little to push it out, but not, you know, not too much, because we don't want to force it too heavily. So it's almost nothing at that level. And then in the veins definitely don't have any pressure in them. They basically channel the blood back to the heart. They end up having thinner walls and wider lumen, wider inside. The lumen is the space on the inside, the open space where blood can go through. So we need then figure out how the heck are these veins going to bring that blood back to the heart. They have valves that open only towards the heart and prevent backflow. And these are, instead of endocardial folds like the semilunar valves, these are endothelial folds that project into the lumen, somewhat similar to the heart valve. So they go like this upward. And so when the blood moves, it moves upward, it cannot fall back, it's gonna not go anywhere. Except when we have varicose veins. Varicose veins are when we have leaky valves, when they get less strong. They don't hold the blood back as much. So the blood goes back a little bit. It falls back through those valves. And so the veins down there stretch a little bit, and that looks like blue veins that show up in the legs. So we have the valves, and then the other thing we have skeletal muscles that surround the veins, squeezing the veins and therefore pushing the blood towards the heart. They call that milking. So the blood, especially down here in the calf, you've got the soleus muscle, and the soleus muscle has a lot of vascularity coming up from the feet, legs upward. And if you go up and you stand up and the soleus muscle contracts, the muscle squeezes the blood vessel, and then the blood has to either go up or down. Since it's valves there, it only goes up. So it gradually moves up towards the heart. So they call that milking of the blood vessel, and instead of the heart being the pump, in this instance we call the muscles being the pump, so they call this a muscular pump. I know it's a little goofy, but that's the way they do it. And it does make some sense. But this is important. I mean, if you're like in an airplane, long airplane ride, now if you're 20, who cares? But if you're 50, we got to start thinking different ways. And you wanna like move your calves. You wanna move up and down. You wanna get up in an airplane and move around, because if you this is all stays stable and doesn't do anything, the blood starts pooling down there. People start getting a little edema in the feet when they're going along airplane rides, for example. And so if you get older, that can be a little bit more dangerous, and then you can have some embolism this large or something like that. So I recommend every time you can get, a couple times in a plane ride or every hour, go to the bathroom or something like that. Doesn't just have to be plane ride, but that's where we notice it. Or the guards in Rome, the Swiss guards, or in England, the Royal Guards, sometimes somebody keels over because they have to stand still, and if they don't push their toes into the boot downwards, they contract that, there is a lot not happening. And so they do that to keep the blood flowing. Anyway, we have one more help. When we inhale, the pressure in the chest drops slightly, causing the large veins near the heart to expand slightly and fill up with more blood. Wow. So when you inhale, the chest inside drops slightly because the air needs to be suctioned into the lungs. But also, the vessels right in that chest area, they expand a little bit, they suction up the blood a little bit towards the heart. And then when you exhale, that goes away. So they call that the respiratory pump. That's the only picture I found. It's kind of good though. You inhale, the blood keeps going. You don't inhale, the blood doesn't move. So I thought that was pretty good for that. That's a kind of an interesting concept though. And the capillaries are where gases such as oxygen or carbon dioxide or substances such as glucose and waste get exchanged. So we have substances and gases in there that can that can get exchanged. Basically, in capillaries, we only have a tunica intima. So that's very, very leaky. That's not stable in terms of keeping all the blood in. So you only have that endothelial layer. Capillaries, so there's what we have here is there's an artery or an arteriole, and then we got one of these big ones going right through there, and on the other side there's a vein, or a venule. Venule just means very small vein. So we have one channel that goes straight through, they call it the Thoroughfare Channel. And then from there, we have these sphincters. And sphincters are little muscles that can contract or open, and they can then determine if blood's going to go through here or blood is not going to go through here, depending on do we need nutrients in this area or do we not need nutrients or oxygen in this area. And so if we need blood, then the blood flows through this stuff. It gets all, into the tissues, and the oxygen goes into the tissues. We can make ATP, and we have glucose. We're all happy. And then when the blood is used up, it gets picked up on the other side and gets pushed into the main channel, the Thoroughfare Channel, and goes then to the venule. So we have capillary beds, creating a microcirculation with fluid exchange. That's important there. And then the Thoroughfare Channel is the mesenteriole. They call that also mesenteriole or vascular shunt. And that connects the venule with the arteriole with the venule directly. So blood always will follow through this channel. There's no sphincter here that cuts it off. There's none of that. So blood always goes through here. So that way we always connect the arteriole with the venule. So we keep the blood flowing. We do have shunts that then go, the offshoots of that mesenteriole, that thoroughfare, have shunts that can be open or closed to let the blood either go through it or not go through it. And opening or closing of those is based on the needs of the tissue at that time. So that can be that's a very, very localized control of where the blood needs to be guided to. First, you got the muscles in the arteries that can contract and relax a little bit to guide the blood to different parts of the body. And then on the tissue level, you have it controlled to that magnitude or that delicate, fine way. And this picture shows when actually there's no blood flowing through. So you see all these are closed. This stays empty. You don't need any blood right now in here. We don't need oxygen. We don't need to get rid of waste. And we don't need nutrients right now. So here we need it, here we don't need it.
So sphincters can be both open and closed?
Sphincters can open and close. Like, the mouth is a sphincter, the eyes, there's a sphincter muscle around there, the Orbicularis muscle. It's sort of the same thing, but it's smooth muscle, and it's in all the tubing, basically. It's in the vascularity, it's in the gut. It's in the bronchi to some level, and the sphincter here are controllable. They basically close when they're relaxed, and they are controllable locally. And so they're just basically, instead of having the muscle through the hole here, the whole artery, you just have a little bit of the same muscle right in this area. Oh look, and there's the lymphatic vessels. They run parallel to the veins, and they help the veins pick up fluid that is pushed out of capillaries. Pick up fluid pushed out of capillaries. Via hydrostatic pressure, that's that blood pressure. So the pushing out of the fluid goes via hydrostatic pressure. But how the heck we gonna let the blood return to the veins? If it's inside the tissue, swept out of the capillaries, how is it gonna go back into a vein? The main driving force returning fluid back to the veins is an osmotic pull. Oh shoot, osmotic pull. Remember that? An osmotic pull is created by large solutes that are left in the capillary. So we also call it the solute pull, bless you. So when we have the fluids get squeezed out of the capillaries, some proteins, larger proteins, like albumin, is staying behind. And it's creating then a higher concentration of that solute, that albumin, the protein in the vessel than on the outside. And that creates a suction. It's like the salt, put the salt under the tomato and the water comes out and creates water droplets. Solutes will pull liquid with them. And so you can create sort of a pulling effect as you have larger solutes stuck in the vessel and you don't have them out here, and then the water wants to go back into the vessel. So that's that part of it. That's the osmotic pull, or the solute pull. It's not strong enough to return all the fluid back to the venous system. See, here is the picture. You got the low osmotic pressure, you just have a few solutes, and then in high osmotic pressure you got much more solutes. We mostly do it like with salt and stuff, but you know, you can do that with all kind of solutes, with albumin too. And what we want to do is, down here we have the hydrostatic pressure is the red arrow, and the osmotic pressure is the blue arrow. So on the arterials, this is the arterial side, this is the venous side. So the red arrow pushes blood out, and the blue arrow, the osmotic pull, brings blood back in. So that's that dual effect. However, the hydrostatic pressure is stronger than the osmotic pressure. And so some fluid will stay behind in the tissues, and that's where the lymphatic capillaries come in. They have valves that open only to the inside. So they got these slits. They got these slits here that are like open, but you can only get fluid going in. It cannot go back out. It gets stuck. And so these opening slits let the fluid enter but not leave. And then the lymphatic vessel from there, they have valves to make sure we don't have backflow. And then they pick up all that stuff from the tissues and dump it into the veins by the heart. And so when we look at the return of the blood from the capillaries to the heart, we always consider the veins bring blood back, and the lymphatics also bring blood back. We know the lymphatic system because of the lymph nodes. You heard the lymph nodes? The ones that swell when you get sick and it hurts? Those are the ones. Oh, look at that, lymph nodes. As lymph nodes are little filters. So they are in the lymphatic vessels, and they harbor a lot of white blood cells in them, and we're going to talk about the white blood cells in a little bit. And then later on we're going to talk about the immune system. And that's all has to do with this. And so these lymph nodes, they create filters where the blood, the lymph, which is that fluid that gets pushed through, that used to be blood, has to go through it. And it's a perfect place for us to figure out, is there some bacteria, is there some viruses, what are we going to do with this stuff? Are we going to get rid of this or not? And so that's what happens in lymph nodes. That's why when we get sick, they swell up, because we have a lot of white blood cells in them, and that hurts. And that makes them tender. So that's what that is about. So it's a very important part of the immune system. I think we'll have that Monday. We're one day behind. You got that after Monday. So we're 1 day behind now. So look at that. That's a picture of a person that everything is taken away except for the blood vessels. You can still see it's a person. So that's a lot of blood vessels that we have. A few of the main ones that we talked about already, some of them we talked about. We talked about the heart here on the left side. The left heart pumps the blood out of the aorta, right here, aortic arch, and then it goes down. That's then the descending aorta, they call that. Thoracic descending. We have, once we pierce the diaphragm, we can call it the abdominal. Down in here, and then look at that. From there we got offshoots. We go to the liver. They call that a hepatic artery. Liver is the hepatic. Hepatitis. Have you heard of hepatitis? That's hepa is liver. Not the HEPA filter. Well, maybe that's good for the liver. I don't know about that. We have some called mesenteric artery. That's a little bit of a special name. That goes to the gut, some of the gut, to the digestive tract. See here, it's also digestive tract. Then we got to the kidneys. We have something called the renal arteries. We got, oh, no, on the other side we got veins. Look at that. The veins look very similar. Well, actually, here's the hepatic. This is an interesting vein, the hepatic portal vein. We'll talk about that. That's the vein that goes from the gut to the vein to the liver to process the food we ate. So that we'll talk about that specifically. That one we don't have an artery for. But look at that. We have a renal vein. And then the vena cava, we talked about it. Then we have the pulmonary. Of course, here it's reversed. The pulmonary is from the lung to the heart. That's a vein. And no, that's the artery because that brings the blood up. It's blue because it's less oxygen, but it's an artery because it goes away from the heart. So on this side, then the red one is the pulmonary vein. So you can check that off there. Make sure you don't confuse that. And then as we get into the inguinal region, it's called the inguinal. Inguinal, but we have the iliac bone here. Sorry, I confused that. We call it the iliac artery for the iliac bone. We have a muscle down here called the iliacus as well. We learned that. So there is a whole bunch of those. I'm not holding you responsible for knowing those as a memory thing, but as a concept, it's pretty straightforward, I think, for the most of them. Because a lot of times in anatomy, after the first runaway through, the next time or the next few times, you're going to go like, does this make sense or not? And if it makes sense, then you don't have to study as heavy. So it makes sense that an artery going to the kidneys is called the renal artery. Once we talk about the kidneys, once we know that we're renal. Or that an artery down here would be called the iliacus artery, the iliac artery. Maybe I have to make sure I don't call it the inguinal. But I'm sure I find a book where it's called inguinal too. And so that's how they make up these names. So let's see, we have more that I want to go through briefly. Oh, that's a big picture. See, look, as we go to the arm, we talked about the subclavian. That's the clavicle. That's underneath the clavicle, subclavian. Then in the axilla, that's the place where it stinks, it's the axillary artery. That's the armpit. Then we have the brachial. How many muscles did we have that are called brachii? Lots of them. That's the brachial artery. The brachial area, the brachial artery. Then down here we got a radius going to the thumb. Remember the radius goes to the thumb. Radial artery. Then the one to the pinky, ulnar artery. And then of course you got tons of small ones you can go detailed if you want to, but that gives you a basic outline to then study the offshoots. Then look at that. We got down here, we got the aorta coming down right here, and then it splits into the iliac, and then we go to the, look at that, it's the femur down, that's a bone, the femur, a femoral artery. There's actually three, look at the superficial, common, well, first the common, then the deep, and then the superficial. See, the common is this here, from here about, and then it splits into two. Then the knee, we studied that the back of the knee is the popliteal area. There's a popliteus muscle actually, we didn't study that. But that's the popliteal area. And then look at that, we got tibials. We got an anterior tibial and a posterior tibial. That's where the tibia is, the shin bone. And then the only one where they haven't updated the name yet is peroneal. That's where the fibula is. That's out here by the fibular. Fibularis, we studied the fibularis muscle. The old name for fibularis muscle is peroneus muscle. So that's that artery there. I haven't changed that name yet. And then down it says pedal, that's PD is foot, so it's in the foot somewhere. Like dorsalis pedis is the top of the foot, dorsum of the foot. But that's, you know, almost detail at the end, because you can start learning the names a little bit and picking it up from that perspective. You know, if you have to pick it up with a multiple choice, then you can pick it up pretty fast. If you have to spell it, it might take a little longer, but it's fine. We'll get to it. And look at the veins, it's most the same. Ulnar, radial, here we got one that's called the cubital. And then brachial, excellent. But look at there's a couple more. We have a basilic vein, we have a cephalic vein. We have not had those. And then down here, they're all similar looking. Don't worry about that. But the saphenous, long saphenous and short saphenous. Long saphenous and short saphenous. So in the veins, we have deep veins and more superficial veins. Arteries are always deep. Because if you have an artery too far on the surface and you cut it, it squirts blood out like in pulsating fashion. You don't want that. So they made sure the arteries go deep. And the veins can go superficial because you cut a vein, you take blood, it's not going to squirt out. That's why they take the blood from the veins. It's not as the hydrostatic pressure, that force is not there. So the deep veins are the ones that are named with the arteries. And the superficial veins in the arm, we got ones called the basilic on the medial side more, and then one's called the cephalic on the lateral side. And those are specific for the upper extremities. These are superficial veins on the upper extremities. So these are superficial. Oops. And in the leg, we have the saphenous. We have the long and the short saphenous. But if you familiarize your name a couple times with the word saphenous, you kind of catch on to it. This is the one they take for heart surgery, bypass. They take the vein out of the leg and put it into the heart. It's enough similar material to do that. And then we got, look at the head, look at that. You can see the whole face practically outlined, and you only have the arteries picked up. That's pretty cool. So when you look at the head is in some ways a little unique because we almost we have a connection. We have two arteries that bring blood into the head. We got into the brain. We got the internal carotid coming from the common carotid down in here. The external goes to the face, and the internal goes into the head and surfaces the front of the brain. And then we have the vertebral artery that goes through the vertebrae. On the outside there, you can see that's where we had on the skeletons, on the spinal cord columns, we see the red going through the neck. That's the vertebral artery. And then from there, it changes names. It's called the basilar artery, but then it feeds the back of the head mostly. But what's interesting is they are connected in something called the circle of Willis. Something called the circle. Why the heck is not on here? Circle of Willis. You don't have to remember that, but if you've written it down, then at least you might have it somewhere written down in your own little atlas. But that's sort of here to try to assure that even though we have a little problem with feeding from here, we're still going to have blood coming from this side that can also feed the back. So it sort of shares the blood a little bit. So that's kind of neat. Good, and that brings me to blood pressure. It is the pressure against which the left ventricle must eject the blood. The right ventricle brings the blood up to the lungs. That's like right there. So we're not going to be too concerned about that. But the left ventricle, we're definitely going to be concerned about that. And that pressure wave can be felt on superficial arteries. So we can go and have a superficial artery here on the inside where we don't really hurt ourselves too much. So we can pick the pulse up here. We can also pick it up here when we measure our pulse after a workout. We can pick up the pulse right in here or up in here. But to take the blood pressure, we usually use the upper arm. So the maximum pressure during a ventricular ejection is known as a systolic reading or systolic pressure, and the minimum pressure during ventricular relaxation is known as the diastolic reading. So when when the heart contracts, it expands these vessels as the blood travels through it with that strong force. And that's the systolic mode. And then when the heart relaxes, we got that elastic recall that keeps pushing the blood forward, but it's much less forceful than that. And so we have a lower reading that we can read. So the way we do it is we have a blood pressure cuff that we put around the upper arm, and we got a stethoscope and we're listening to the artery, and we're going to pump that sucker up and inflate the cuff with until we don't hear any pulse or anything. So we go up to like 180 or something, and then we slowly let the pressure go and let it release. And with the stethoscope, we listen into the elbow area, and we hear a pulsating. And when we hear a pulsating sound, we see the start of the systolic pressure. So as the blood cuff squeezes this together so nothing can go through. And then as we let it go, at some point when the force is really strong and the heart pushes hard, a little bit goes through and we can hear turbulence. Like in a river, if the river gets narrow, the stuff from the outside starts circling. It's the same thing, that's turbulence, like blood circling around. So then we start hearing the boom, boom, boom. We can hear the pressure against it. At some point, we let it go enough that we cannot hear any more expansion because the vessel is open enough. It's not pushing it further open. And then that's the second reading, that's the diastolic reading. Normal resting blood pressure is 120/80. Once it's 140/90, they call it hypertension. Now they've been pushing that number downward, and some circles think there is logic to that. Some circles think there is medication selling logic to that. And we just have to sort of work with our doctor. But blood pressure, high blood pressure is certainly one of the problems that we encounter in our society. In part, it's the stress that we're exposed to continuously. We know that, for example, cholesterol readings are higher at tax accountants during tax season, which is now, I guess, ish. And of course others, that's just the one I remember from the book by Dean Ornish. Dean Ornish is a person you want to know when he talks about blood pressure. You want to, if you have your own problems with it, like I do have some with it, you want to read him. He is a guy that started studying this in 1975 when he was in medical school. And he got Medicare to pay for a preventative program for reversing cardiovascular disease instead of using medication. He has Medicare paying for that. You know, if Medicare pays for something, they got to go to Congress, they got to go to the Senate, they got to talk about it, they got to make sure it works out. And there's no preventative program ever been approved except for him. And he's done research also with, I forgot her name, a woman in Stanford who got a Nobel in medicine for reversing aging with the telomeres, with the end of the DNA spectrum that gets chopped off, and how to reverse that a little bit. So very, very interesting guy, and also funny the way that he writes. It's very good. And he talks a lot about, you know, the emotional component and the food component, fat and salt, and carbs, refined carbs. Actually, he's big on that. So his diet has been, since 2011, his diet has continuously been the best heart disease diet that has been recommended. And of course, then the other thing is cardiovascular health. I mean, the other thing is exercise. And that's what we're talking about, doing some pumping exercise where we get a sweat. But I just want to mention that briefly because blood pressure is a big problem in our society, and medicine is sort of doing a job with dealing with it. You know, some good, some not so good, but just everybody needs to be on cholesterol lowering drugs. It might be not so good when a Dean Ornish says, we don't even know if the connection is that strong. Then I'm listening to that. Oh, here, pulse pressure, sorry about that. So 120 is the systolic reading, the 80 here is the diastolic reading. The pulse pressure is the difference between the two. So here it'd be 40. As the arterial walls decline in elasticity, we have arteriosclerosis happening. That first rises that will raise the diastolic blood pressure first, followed by a later systolic blood pressure reading, which then remains high even when we're at rest. So that's interesting. So when the diastolic blood pressure goes up at rest, then we're more thinking long-term stuff, more generally, versus if just the systolic blood pressure is high, because you might have been just running around. Maybe you're just freaking out because you were caught off on the freeway by some stupid ass when you were driving to the doctor or something like that. And so, and sclerosis means heart. So that's a hardening of the vessels, of the arteries. That's what that means. And you can see it up here. That's arteriosclerosis, where you see the plaques. These are the plaques. That's what we're talking about. And they're right underneath the endothelial layer where they build up, these foamy cells. Okay, let's see if we got that taken care of. No, we got that. Good. So that's the first part of this whole session today.